Magnetism and Quantum Locking. I'm Shiming Lee.
I'm Vargo Urla.
And I'm Hamza Gujar.
And this is brought to you by Mr. Johnson's IB Junior Class of 2013. So today's topic deals with magnetism and a marvelous phenomenon. But before we go into depth, Vargo, why don't you give a brief intro to magnetism in general?
Sure thing, Shiming. Magnetism is created by a charged particle moving with a velocity. Magnetic fields create magnetic force, which is the attraction between opposite poles on a magnet. Hamza, what was the formula again?
Magnetic force is equal to the charge times the velocity times the magnetic field times sine of the angle.
And don't forget, magnetic fields passing through a conducting loop induce magnetic flux.
Now this formula I know. In a conducting loop, flux is calculated by multiplying the magnetic field times the cross-sectional area of the loop times cosine of the angle.
Alright guys, I think we get the idea. Let's get into the fun stuff, quantum locking and quantum levitation. I think it has something to do with magnets and superconductors. Take a look at this video, for example.
Superconductors, you say? What is that exactly? Bargodina?
Well, Shiming, superconductivity is a quantum state of matter. It's a phenomenon of exactly zero electrical resistance, expulsion of magnetic fields occurring in certain materials below critical temperature.
Wait. You say electrical resistance? Yeah, we learned about that in electric statics, right?
Mm-hmm.
There's no friction, no heat loss.
Well, Hamza can tell you about that.
Hamza, you want to talk about?
Yeah, sure. Since superconductors despise magnetic fields, they would try to expel all the magnetic fields from the inside by circulating currents. These currents would cancel out all magnetic fields that would come in contact with the superconductor. For example, take a look at the picture. The magnetic fields are dispelled.
Wow, that's cool.
Yeah, man.
I know.
But sometimes strands of magnetic field can get stuck inside a superconductor. And in that case, they're quantized, which means they become discrete units that behave like particles. So we call them fluxons, because they're particles of magnetic flux.
But really, they're little quantized of magnetic flux. It's a proper terminology for it.
Yeah, but, I mean, fluxons, that just makes sense, right? Such
Flux.
creativity, then maybe.
Fluxon? The picture shows beautiful fluxons right there.
Yeah, they do.
Now, you put the superconductor inside a magnetic field. The material doesn't like the fluxons to move, because that would create resistance.
And here's the coolest part, guys. The object will lock the magnetic fields in place, which produces a special phenomenon called the Meissner effect, allowing the superconductor, in essence, to be levitated.
Whoa.
Levitated? With magnets?
I know, that's so cool.
No way.
Yeah, this just shows what modern technological advancements have allowed us to accomplish. For one, we can see clearly the Meissner effect in the maglev train. The train is locked onto the magnetic track and can move freely along the track.
So that's why that train appears to be floating. I see.
Yeah.
The main idea is that these superconductors can produce such strong currents in magnetic fields. They've been used in MRI machines, particle accelerators, and for energy storage. All great uses and
I know. Wait,
futuristic examples.
I just realized maglev stands for magnetic levitation. Mind blown.
Really? I didn't know that.
Wow. And that 3-inch disc can lift 70,000 times its own weight. I can finally have superpower and lift cars in my hands.
Alright, before we go, I just have one last question. What did the male magnet say to the female magnet?
What?
From your backside, I thought you were repulsive. However, after seeing you from the front, I find you rather attractive. Alright, that's it for today.
Sweet.